Hi, I'm Kate, and this video is for Lab 1 for Physics 2211. The lab's purpose was to focus on Newton's second law, which states that the acceleration of an object depends on the net force acting on the object and the mass of the object. A non-zero net force causes acceleration. However, since the normal force of the table acting on the object is equal and opposite to the gravitational force, there was a zero net force acting on the object in motion, resulting in a constant velocity in the simulation and a non-constant velocity in real life. But why is that? In this lab, the system was the object and the ramp. The surroundings are everything else surrounding the object and the ramp. As seen in the code for the simulation, force is calculated by mass multiplied by acceleration. This comes from Newton's second law. This code comes with the assumption that the only forces working on the object are the normal force and the gravitational force. This can be seen in the y component of the force, in which mass is multiplied by the acceleration due to gravity, then subtracted by the same amount since the normal force is equal and opposite to the gravitational force based on Newton's third law. The initial velocity of the beginning of the simulation is taken from the instantaneous velocity from the tracker. This is the velocity the object is first at when it begins motion. The velocity is only seen in the x component since the ramp is a flat surface. Acceleration due to gravity is identified as 9.8 meters a second squared, and the mass is identified as 1 kilogram. Now again, this is equal and opposite. The initial position also came from the initial position seen in tracker. This loop in the code adjusts the velocity using the velocity update formula based on a non-zero net force. Since F equals ma, acceleration would logically be force divided by mass. Once the force is divided by mass, the acceleration must be multiplied by the change in time to get the final velocity, since acceleration is in meters a second squared and the velocity is in meters a second. This is then added to the initial velocity to get the final velocity. The final velocity is then multiplied by the change in time as well to get the meters of position moved. This is then added to the initial position to find the final position. That being said, these are the resulting graphs and simulation for this data in the specific code. In comparison to real life, the object was rolled and ended up not going as far as the simulation based on the graph. It can be seen that the ball showed a different velocity graph as well. Why is that? As mentioned, the simulation only accounted for the force due to gravity and the normal force. However, there is one very important force to remember, which is the force of friction. Friction causes a non-zero net force to occur on the object in real life, which results in an acceleration that is negative. As a result, the object begins to move slower. If I had used the final velocity from the real-life experiment, the simulation would have shown less movement since friction had acted upon it. That being said, other errors also could have occurred. Mismeasuring the size of the object could have impacted calibration and tracker. If the surface wasn't flat as we thought, there could also be issues with gravity acting upon the object. Finally, there's also the axis and tracker, which could have been misaligned with the object itself. That being said, what if the x-axis was flipped to the negative x direction? Instead, the results would primarily be the same, however, it would all be in the negative direction. The acceleration would be backwards instead of forwards. This is important to understand when setting up tracker. Even though the magnitude of the movement will always be positive, the actual position will be negative. In regard to the net force, it is possible to say how many pushes and pulls are acting on the object. However, the magnitude of those forces is much harder to predict. Air resistance, friction, and the initial push, and the contact forces of the object with the ramp are all variables that have to be taken into account when talking about the forces acting upon the object. While it is easy to discover the net force from the deceleration of the object over time, the actual individual forces would be nearly impossible to distinguish. The computational model only infers the two forces acting on the y component that cancel each other out, resulting in linear motion. That being said, this lab looks at how the real world differs due to various invisible forces that work around us. Thank you so much for watching, and I really hope that you enjoyed it.